Here's a quick video on visualizing electric fields with respect to charged particles. So here, let's start with a quick simple example. Here's your XY plane, and suppose we put a charge over here in the middle. Let's call this a charge Q. Now this charge Q can either be positive. Now if this charge is positive, we know that electric fields will point away from it. Now if that same charge, let's say, is less than 0 or a negative, we know the electric fields will point towards it. Some people like to say that, okay, wherever there exists a positive charge or a negative charge, its opposite must also exist, in lieu of conservation of charge. So electric fields will always point from positive to negative. However, we can also use the more naive picture that I have just presented here in green. So, without further ado, let's consider an arbitrary point in space. Let's consider, let's say, this point over here. Let's call this point A. And for argument's sake, let us say that Q, for the time being, is positive. So, if we say that here Q is a positive, we know electric fields will point away from it. So extending a line from the charge to the point in space known as A, we know that the electric field at point A must point away from it. So we'll call that electric field E. So how do I describe this vector? Well, if we know what the coordinates are for point A, let's say they are XA and YA, we can then go ahead and see that there's a right triangle here that we can exploit. And we can define this angle theta over here to allow us to determine what the direction of this electric field is, given that we can describe the magnitude of that electric field just using Coulomb's law. So here I can break down this vector into its x components, call it E sub x, call the y component E sub y, and we see that this angle theta again pops up right over here. If I extend this imaginary parallel line along the direction of E sub x. Okay, next I can translate the EY component over here, and what I see is I've actually formed a triangle. Now let's take this triangle out. Okay, looking at the legs of this triangle, we see we have the x and y components of the electric field, the magnitude of the electric field, which is E, is defined by Coulomb's law. So E times K, Q over R squared. And this here is just the magnitude of the electric field. And that's here is just the magnitude of the electric field, where K is a constant, Q is the value of the charge, and R is the distance from the location of the charge to the point in space we want to know the electric field. Okay, how do I express this as a vector? Well, you should now be familiar with I and j components. So E is equal to Ex I hat plus Ey j hat, where the I and j components correspond to directions or parts of the electric field vector in the x and y direction. Note the bar over the electric field on the left-hand side. That's how we can typically indicate a vector. Other texts use a different notation, but that's the one I will subscribe to here. Okay, so what is the x component and what is the y component? Well, if we take a look at our triangle that we've just drawn over here, we see the one in the x direction is E times cosine of theta. The one in the y direction is E times sine of theta. So I can just as well take these two components and substitute them into my vector, over here. So now I see my electric field vector is equal to E cosine of theta I hat plus E times sine theta of j hat. Now, what is E? Well, I already know what E is. E is something we've already determined. It's this quantity over here. Now, before I plug it in, let's try to do some simplification first, just for the sake of ease. I see that E is in common in both components of these vectors, so I can just as well factor them out as a scalar. So cosine of theta I hat plus sine of theta j hat. And that's pretty much it. Now let's go ahead and plug in what E was. We see E is equal to k times q over r squared times cosine of theta I hat plus sine theta j hat. Okay, there's a problem here. What is r? Recollect that r is the distance between the charge and the point in space we're interested in. So let's go back to our diagram over here. We notice that if we know what the coordinates are for point A, and we know that the point charge is located at the origin, and that the distance between them can be determined using the distance formula, or in this case, by looking at this triangle over here, we can use the Pythagorean theorem. And we see that that distance r from the charge to point A is described as xa squared plus ya squared, which are the x and y components or coordinates of point A, square root. And that's pretty much it. So let's go ahead and plug this back in. So now we see this is k times q over xa squared plus ya squared square root times cosine of theta I hat plus sine theta j hat. We can also do a little more work here too. For instance, cosine theta and sine theta. If we take a look at these two components carefully, if we don't know theta, we can always exploit the fact that we know what point A is, xa, ya, or we could say what the legs of our triangle are, that describes the distance from Q, the point charge, to the point in space A. And it's described by this right triangle. We can exploit the properties of a right triangle to substitute for cosine theta or sine theta, should we not know what theta is. And if we should know what the magnitude of the hypotenuse is. Okay. So with that, in the next video, we'll try to consider multiple charges. Now, here, let's keep talking about the single charge. If we go back to our picture, this was okay, all under the pretense that we said that the charge was positive. Now, what happens if we have a totally different scenario where the charge instead is negative? Well, that's not so bad. If we say the charge is negative, then the electric field is just going to point in the opposite direction. As a result, we see the components would point in the opposite direction of the components of the electric field as if it were positive. Hope you can see that. It's a bit messy, but that's why I color-coded it. Hopefully it makes sense. Okay, so on to the next video.